Let's go ahead and get started. Like I said, today we're going to be talking about vapor pressure. And so essentially vapor pressure has to do with if you have, why is it not writing? Oh, because it's white. All right. So if you have a liquid that's in a container or a sealed container of some sort, so we have our liquid here, and anytime, have you ever noticed like when you close a water bottle or you have a water bottle that's been closed, when you first open it, what does it do? It makes that little sound. All right, guys. So as you're when you have any type of liquid at a given temperature, some of the vapor molecules or some of the molecules are going to escape into vapor. So that's why like a closed water bottle or any kind of closed bottle will produce some pressure in there. Even though we're not causing it to evaporate per se, we're not heating it up to evaporation point, we're just because it's closed, some of the particles in this liquid are going to escape as a vapor. And that is solely based off of this concept of vapor pressure. So the definition, and you can highlight it or whatever, vapor pressure is the pressure due to particles of a substance in the vapor phase above its liquid phase in a closed container at a given temperature. So we're going to have a certain amount of water molecules. If this is water, we're going to have a certain amount of water molecules in the gas phase that are above this. And so the weaker the force holding the liquid together, the higher the vapor pressure. So we would expect nonpolar molecules to have the highest vapor pressures and hydrogen bonded polar molecules to have the lowest vapor pressure. Well, ionic is not going to form a liquid. Ionic's got such, they're going to form salt. So we can put them in solution. And I guess, yes, that would somewhat affect it, but we don't really look at vapor pressure with an ionic solution. Yes? Because the hydrogen bonds, this molecule is going to form hydrogen bonds with each other. So that IMF is stronger. So the stronger the IMF, the more likely they are to stay closer together. No, it's going to have a lower vapor pressure. Basically the higher the vapor pressure, that means it's the easier it is for it to turn to a gas. All right. So let's look at this in terms of molecules in relationship to this graph. So this molecule right here, C2H5O2, no, C2H520, is what's called diethyl ether. Diethyl ether. All right. This is one of the first anesthetics that were used to put people to sleep during surgery and things like that. One of the things about it, it has an extremely high vapor pressure. So think about it. Normal atmospheric pressure at sea level is 760 millimeters Hg. So what that's saying is this is going to be a gas at 0 degrees Celsius. This would be a gas with any trying to think how to say this. So anything, how am I going to say this? I'm trying to think. Okay, at around 250 millimeters Hg, this is going to be a gas. Anything above, we would have to really, really drop the pressure to get this to turn into a liquid or a solid or anything like that. I guess is how to say that. So So let's just kind of look here. Why is this so readily, why will this right around here is room temperature. Why will this so readily be a gas at 24 degrees Celsius or 30 degrees Celsius? Well, no. What type of molecule is this? It is a covalent molecule. Actually, there's an O in there. It is a nonpolar molecule. So what's the only forces holding these together? London dispersion forces. So this has very weak IMFs. So they're not super attracted to each other. So this is going to turn to a vapor very easily. Now, this one right here, what do we notice on this group? It will have a hydrogen bond. It is a polar molecule. All right. And then this one is a polar molecule that's going to go hydrogen bonds as well. But why will this one have a lower vapor pressure? This one is going to be more polar. All right. This one is polar because it has the hydroxide on it, but this one is even more polar because that's it. It is only the hydrogen bonds on it. All right. So the more polar the solution, the lower the vapor pressure. So here's the overall statement I want you to have. The stronger the IMF, the lower the vapor pressure. All right, so the way I want you to think about this, in order for this water to turn to a gas at 24 degrees Celsius, about right here, we would have to drop the pressure almost all the way down to 0. But for this substance to turn to a gas at 24 degrees Celsius, pretty much, or to hold it at a liquid, the pressure has to be, well, I mean, anything above, anything greater than 500 degrees, not 500 degrees, anything greater than 500 torr or 500 millimeters Hg, this is going to exist as a gas. So if we drop the pressure all the way down to 500 millimeters Hg, then it would start being a liquid. And that's kind of how to think of this. So this is telling us when it's a gas, at what pressure would it turn to a gas. And we'd have to keep lower and lowering the pressure to get it to turn to a gas. So just kind of think of it in that relationship. Yes? The lower the pressure. So think about it like this. If you have, y'all remember, or have any, y'all have all seen dry ice, frozen carbon dioxide. All right, what does frozen carbon dioxide do at regular atmospheric pressure and room temperature? It vaporizes, it sublimates. It goes straight from the solid to the gas. All right, in order for us to keep dry ice at a solid, as a solid, what do we have to do? We either have to keep it really, really, really super cold, or we have to lower the pressure of the container. So if we get it to a low enough pressure, it'll stay stay in that solid. Yeah. And so that's kind of how to think of it. So it'll stay a solid as long as the pressure is low enough. All right, moving on. Um, so looking at these two containers, one of the things that we have to realize is when we put a liquid in a container and seal it off, it doesn't automatically go to its equilibrium vapor pressure. So when we first put it in there, there's not very much pressure. So I take this container, and put a certain amount of liquid in there, and I cap it off. Well, right now the pressure is still atmospheric pressure. In order for it to have that vapor pressure, in order for it to reach equilibrium, it has to sit for a little while. So if I take it off right now, there's not going to be any pressure release. But if I let it sit for a few hours, and the way this lid works, we're not really going to hear it because it's such a big container, but if I let this sit for a few hours, it will equalize. The vapor pressure and the gas pressure in there will equalize, and then when you open it, you get that little bit of a, you know, like a drink can or whatever. All right. And same thing when you pop the top on a Coke can and all of that. They don't pressurize that can. It's having to do with the carbon dioxide that escapes from it as it's sealed. That vapor pressure, and then when you pop the top, then more of it releases because now it can be reached, the pressure in the can drops. All right. So in order to represent this mathematically, to determine the vapor pressure at equilibrium, we would use the Big Mama equation, the in and out and all of that. But we would have to, so it's basically going to be represented something like this: H2O So at equilibrium, what we would have is the H2O at liquid is at equilibrium with the H2O at gas. In other words, we have as many molecules escaping as we have going back to a liquid. Here, the vapor pressure is greater, so here we have more molecules escaping and none of them going back in. So when we first started off, we're going to have a higher water line or a higher liquid line, and then as more and more molecules escape, the line goes lower and lower, and then when we reach equilibrium pressure, or when we reach equilibrium, the volume line has decreased a little bit, and then we have this transfer from liquid to gas, gas to liquid, and it's at an equal state. All right, so here's kind of an example of some questions you might see on this. The pressure of a vapor present at equilibrium. The system is at equilibrium when no net change occurs in the amount of liquid vapor because the two opposite processes are exactly balance each other. So the question that we might see is, what is the vapor pressure of water at 100 degrees Celsius? So what do we know that's happening at 100 degrees Celsius in water? That is the boiling point. So what is it doing at 100 degrees Celsius? It is vaporizing. So assuming that we are at sea level with 1 atmosphere of pressure, what is the vapor pressure of water at 100 degrees Celsius? If it's completely escaping at that, what does the pressure have to be? Yeah, that's right. That's right. Sorry. You said I said 1 atmosphere, and then you said 760. It caught me off guard. So basically, what I want you, the way we would answer this. So we have our little system here. So what we're showing is that the pressure of the water molecules escaping is going to be equal to the pressure pushing down on it. So here's your advanced definition of boiling point. Boiling point is when the atmospheric pressure is equal to the vapor pressure. Has anybody ever used one of those vacuum seal containers to put like food in it to take up food after you've heated up or anything like that? Yeah. If you ever get the opportunity to use one of these, it's pretty neat to kind of watch this. So like we used to, whenever we would cook a roast or cook beef stew or whatever, we had one of those containers that you suck, it has a little vacuum sealer, and you suck the air out of it. So we would wait until it cools down to like room temperature. Then all of a sudden you reduce the pressure inside that container, and if you watch it, it'll look like the liquid that's in there with it will start boiling again. So as you reduce the pressure, or as you reduce the atmospheric pressure inside that container, it starts boiling. A pressure cooker works on the same phenomenon. Pressure cooker doesn't have to get that hot, but as you remove pressure, it increases the heat, or not increases the heat, but it increases the escape velocity of those molecules. So it basically boils at a very low temperature. Um, mm, more like if you go to if you try to boil water here, it's going to boil pretty close to 100 degrees Celsius. But if you go to Colorado and boil water, it boils more like at 95 degrees Celsius because the pressure is so much lower, so the atmospheric pressure and the vapor pressure are equal, so it doesn't have to get as high of a temperature. Yes?
You're just saying that by manipulating the pressure, you can change the boiling point of any substance?
Yeah, you can make it boil at a lower temperature. Yeah, so the more you reduce the pressure, the lower the boiling point is. The lower the temperature boiling point of it is. If you increase the pressure, so if we were on a submarine, if we were in a submarine and trying to boil water at the bottom of the ocean, you're going to have to get it at a higher than 100 degrees Celsius.
Wait, wouldn't the inside of the submarine be atmospheric pressure?
You're going to feel some of the. So no, I'm assuming an unpressurized submarine. Uh, so yeah, if we could exist at the pressure that exists on the seafloor, but you are going to be in somewhat of a pressurized situation anyway. So when you say you're at 1.5 atmospheres or 2 atmospheres, it's going to raise the temperature that you have to boil at. Yes. It should, because that should manipulate equivalently.
So if I were to like make ice cubes in a submarine, would it be easier?
It should be easier. Yes. Yes. Basically, because we have to get the molecules excited enough that they can escape. Yeah, and they can start. Yeah, they start boiling whenever those two reach equal. So, if as you increase energy, you're causing more and more of those molecules to escape. That's why if you were to take something, put it on a hot plate, and start boiling the water, the temperature is going to stay at 100 until all of it boils off, and then the temperature will start raising again. All right, um, so to answer this question, this is just an advanced definition of boiling point. To answer this question, the vapor pressure of water at 100 degrees Celsius is equal to the atmospheric pressure. We already said that. All right. So looking at these are some. These are what barometers used to look like. Most of the time, you'll see the barometers that are just a little dial that's on your wall, or just a readout. I have an older barometer here. I think this one is. This barometer is probably about 30 years old. It's very expensive, but we have a temperature thermometer here, and this part is the barometer. And if you ever get the opportunity to come over here, you can see the mercury in the tube, and so like this room's usually right around 750 millimeters Hg, millimeters mercury. So 750 torr in this room. We are just a little bit above sea level here, so that makes sense for that change. And then also, for whatever reason, because of the air conditioner system in this building, it's kind of a low pressure building. So it always kind of feels like we're in low pressure. All right, now looking at these. So what do I expect you to know about this? All right. So in this first tube, this is what happens whenever we take this tube and we create a vacuum in it, so there's no air in this, and then we invert it over a source of mercury. Well, if that happens, we're going to suck up, or we're going to cause this column of mercury to rise up to 760 millimeters of mercury. So we have atmospheric pressure pushing down on the mercury here, causing it to rise up in the tube because there's no pressure here. All right. If we were to fill this with water vapor and do the same thing, we're only going to draw up 736 millimeters of mercury. And that's because the vapor pressure of water at standard temperature is 24 torr. So we can determine that it's 24 torr based off of, when we do this experiment, we would raise it up 736 millimeters Hg. We subtract that from standard pressure, and then we would get 24 torr. So
How would you feel that with water vapor? Like, how would you know how much to put in so you could still something?
I don't know. I guess it's people that are much smarter than I that do that. I'd have to look it up. I'm sure there's an exact process. Well, because this only can push down so hard. And so kind of like this all has to do with kind of like water pumps and all of that. You can take a pump and it can only suck a water column up so high because the atmosphere is only going to help you so much. Atmospheric pressure is only going to help you so much, and then the pump can only draw so high. So yeah, like when he gets caught in the tube and all that, it's a similar principle. It can only push it up so high, so that tube can only be so long before you have to level it off and then do another set of pumps. So same thing here. This vacuum, even though we've removed all of the air in here, that column is only going to go up to that height. Yes?
So the 2465, like 545 torr, that's its max
That's at standard pressure. So if we brought this below sea level, this column is going to go a little bit higher. If we brought this one below sea level, this column is going to go a little bit higher. But then this number would be different. Our starting number would be different. So just kind of thinking about what we know about this molecule, this is an extremely polar molecule, and it's going to form very, very strong H bonds between each molecule. So that's why this is going to be such a low vapor pressure. There's nothing here, so this is going to be as dense as it gets because there's nothing to prevent it from rising here. There's a little bit of pressure to prevent it from rising here. This one is a little bit weaker of a polar bond. So the IMFs here are going to drop it a little bit more, so we get 760 minus 695, which gives us 65 torr. And then this is a very nonpolar, and it's only experiencing London dispersion forces, so we see a real high vapor pressure, so it's going to push that mercury column way down. And so we see that we have like 545 torr. All right, so that means it's going to go to that vapor way easier than anything else. Now, most they'll ask you to do is they'll give you a column height, and you need to determine what's its vapor pressure, and you just simply do that by subtracting it from the standard pressure. All right, so this chart is the same chart as before. It's just nice and in color and a little, computer generated, so the curve's a little cleaner than what this chart was before. So those two are the same charts. It's just this is more like one that you would see on a test or on AP. The other one is more like I would give you for something, or you would create in the lab. And so this compares, again, temperature and pressure. As the temperature increases, the pressure at which it vaporizes also increases. So the more excited the molecule, the more likely it is to be a gas or a vapor. All right, so here is what I wanted to get to today. Clausius-Clapeyron equation. All right. So this has a natural log in it. So just to kind of go through it here. So we see that we have the natural log of vapor pressure at temperature 1 over vapor pressure at temperature 2. You're not going to put the temperatures in here. You're only going to put the pressures that exist there. Is equal to the delta H of vapor over R, and this is the energy R. And so that's going to be the 8.314 joules per Kelvin mole. Remember to keep your temperatures in Kelvin, so we would do 1 over T2 minus 1 over T1, and then solve. So let's look at an equation of how we would do this. All right, so just keep that equation available for you to use, and we'll set one up, and we'll actually do one together, hopefully from the homework sheet, that we can do one together so you can see it too. All right, so we have a question. The vapor pressure of water at 25 degrees Celsius is 23.8 torr, and the heat of vaporization of water at 25 degrees Celsius is 43.9 kilojoules per mole. Calculate the vapor pressure of water at 65 degrees Celsius. So 25 is our T1, 65 is our T2. We do need to convert to Kelvin and all of that. So let's set this up in our equation. Now, One thing to notice, our energy R, what unit is it in? So it's joules per mole K, or K mole. All right, what do you notice about this one? It's kilojoules, so we need to convert that to joules. All we would do is multiply it by 1,000. When we put it in, that's just something to pay attention to when you put it in to solve. You're going to want to do that first. So setting this up, we have the natural log, ln. So we have 23.8, sorry, 23.8 torr. Do we have a second pressure? No, that's what we're solving for, P2. So that's going to be equal to delta H, which is 43.9, so 43,900, right? Joules per mole over R. I don't know why I wrote the delta H there. That's just in the way. Over our R, which is 8 point what? 3145, I guess we can put that there. And that's going to be joules per mole K. All right. Times 1 over. And so temperature 2 plus 273, so 65 plus 273 is what? And then 25 would be 298. You didn't have to put the parentheses around it. I was just... So in order to solve this, first thing I'd want you to do is go ahead, solve this side of the equation. All right, we're going to leave this side alone, so we end up with ln 23.8 all right, natural log 23.8 divided by P2 is equal to what? What do we get on the left side? Sorry, I'm going to open up my calculator because I want to show you all how to do this. All right, so ultimately you come up with 193.7 torr. So let's let me All right, so looking at our homework sheet real quick, we have diethyl ether. Diethyl ether was one of the first chemicals used as an anesthetic. At 34.6 degrees Celsius, diethyl ether has a vapor pressure of 760 torr. And at 17.9 degrees Celsius, it has a vapor pressure of 400 torr. What is the delta H of vaporization for diethyl ether? All right, this one is a little bit easier to solve than the last one, but basically we're going to have natural log. What is our P1 Pressure 1.
760.
760 torr. So we're going to put 760 torr on top. Divide it by 400 torr. All right. Then we set it equal to delta H, which is our unknown, 8.3145 times 1 over 34 points. No, it's going to be, so this is T2 because it's always final temperature minus initial temperature. It should be T2 minus T1. I did that backwards. That was my bad. All right, so 17.9 times plus 273 is, I don't have my sheet where I was working this out. 290.9 minus 1 over, is it like 3? All right, and then go ahead and solve for delta H. Yes. All right, so I'm going to have to set up a preface on this one that this is only for my students to use because I made a lot of errors in this one.